Kirchoff's laws. Kirchoff's laws are some of the fundamental laws that find applications in electrical engineering for formulating the circuits. Kirchoff's circuit laws lie at the heart of circuit analysis, and were introduced by German physicist Gustav Robert Kirchhoff in mid-1800s. With the help of these laws, and the equation for individual components like resistor, capacitor, and inductor, we have the basic tool to start analyzing circuits. There are two laws that make up the Kirchoff's law, and they are Kirchoff's current law, Kirchoff's voltage law. Kirchoff's current law is also known as Kirchoff's first law, or junction rule. The principle of this law is to conserve the electric charge. Kirchoff's current law states that, for any node in an electrical circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. A node is a point, or a junction, where two or more circuit elements are connected. If only two circuit elements are connected to a node, then it is said to be simple node. If three or more circuit elements are connected to a node, then it is said to be principal node. Mathematically, Kirchoff's current law can be represented as where Im is the branch current leaving the node, M is the number of branches that are connected to a node. The above statement of Kirchoff's current law can also be expressed as the algebraic sum of currents entering a node is equal to the algebraic sum of currents leaving a node. Let us verify this statement through the following example. In the above figure, the branch currents I1, I2, and I3 are entering at node P. So, consider positive signs for these three currents. And the branch currents I4 and I5 are leaving from node P. So, consider negative signs for these two currents. The Kirchoff's current law equation at node P will be I1 plus I2 plus I3 minus I4 minus I5 equals 0. That is, I1 plus I2 plus I3 equals I4 plus I5. Here, the left-hand side represents the sum of incoming currents, whereas the right-hand side represents the sum of outgoing currents. Sigma I incoming equals sigma I outgoing. Here, we considered negative sign when the current leaves a node, and positive sign when it enters a node. Similarly, we can consider positive sign when the current leaves a node, and negative sign when it enters a node. In both cases, the result will be same. Note: Kirchoff's current law is independent of the nature of network elements that are connected to a node. Kirchoff's voltage law, KVL. Kirchoff's voltage law is also known as Kirchoff's second law, or loop law. It is one of the fundamental laws used in circuit analysis, and is useful for finding potentials in current, when simple analysis is insufficient. Kirchoff's voltage law states that at any time instant, the algebraic sum of all branch voltages around any closed path of a network is 0. Now, let us understand this law by taking an example of a simple circuit with a battery connected to three loads. The loads are labeled as L1, L2 and L3, and battery has a voltage VA. We know that a resistor will have a voltage drop across it when connected to a battery. We labeled the voltage drop as V1, V2, and V3 for loads L1, L2, and L3 respectively. In this circuit, we consider voltage to be positive when it is added into the circuit, and negative when it is taken away in the circuit. Here, battery gives voltage to the circuit, and taking that voltage VA as positive, and each of the loads have voltage drop across them, and we take those voltages as negative. As per the Kirchoff's voltage law, the algebraic sum of each of these branch voltages, VA, V1, V2, and V3 will add up to 0. This means VA minus V1 minus V2 minus V3 is equal to 0. Let us take this equation as equation 1. Now, let us further understand how Kirchoff's voltage law works. We can assume that a charge Q is flowing through the closed network. As battery is giving energy to the circuit, the charge Q picks up an energy equal to Q times VA as it moves through the battery. As the charge goes through the loads, this energy is consumed by the loads. So, the energy lost by each load is equal to the charge times the branch voltage across the load. This means that the energy lost while the charge is going through L1 is equal to Q times V1. Similarly, the other energy lost are Q times V2 and Q times V3. By the law of conservation of energy, the charge will have zero energy as it returns to the negative end of the battery. That is, VA, Q minus V1 Q minus V2 Q minus V3 Q equals 0. Dividing both sides of the equation by Q, VA minus V1 minus V2 minus V3 is equal to 0. This is the same equation as equation 1. So, we have proved Kirchoff's voltage law. Note: we applied Kirchoff's voltage law to one loop in the previous example. But, in reality, we can apply it to a network with any number of loops. Applications of Kirchoff's laws. They can be used to analyze any electrical circuit. Computation of current and voltage of complex circuits. Advantages of Kirchoff's laws. Calculation of unknown currents and voltages is easy. Simplification and analysis of complex closed-loop circuits becomes manageable. Limitations of Kirchoff's laws. The limitation of both of Kirchoff's laws is that it works only under the assumption that there is no fluctuating magnetic field in the closed loop. Electric fields and electromagnetic field could be induced, which causes the Kirchoff's loop rule to break in presence of a variable magnetic field. To know more, sign up to www.lynxe.in.